हेलो एवरीवन। तो यहाँ पे हम लोग चैप्टर 2 कैन बी यूज टू प्रोड्यूस इलेक्ट्रिकल एनर्जी कन्वर्जनली। इलेक्ट्रिकल एनर्जी कैन बी यूज टू कैरी आउट केमिकल रिएक्शन दैट डू नॉट प्रोसीड साइमल्टेनियसली is the study of production of electricity from energy release during spontaneous chemical reaction and the use of electrical energy to bring out non-spontaneous chemical transformations. The subject is of importance both for theoretical and practical consideration. A large number of metals, sodium hydroxide, chlorine, fluorine, and many other chemicals are produced by electrochemical methods. Batteries and fuel cells convert electrical energy into chemical energy and are used on a large scale in various instruments and devices. The reaction carried out electrochemistry can be energy efficient and less polluting. Therefore, the study of electrochemistry is important for creating new technologies that are eco-friendly. The transmission of sensory signals, those cells to brain and vice versa, and communication between the cell are known to have electrochemical origin. Electrochemistry is therefore a very vast and interdisciplinary electrochemical cell. We have studied the construction and functioning of Daniell cell. This cell converts the chemical energy liberated during redox reaction. Zinc plus carbon copper ion gives zinc ion plus copper. To electrical energy have an electrical potential equal to 1.1 volt. When concentration of zinc ion and copper ion is unity 1 mole decimeter cubic, external opposite potential is applied in galvanic cell and increase slowly. We find that the reaction continue to take place till the opposing voltage reaches the value of 1.1 volt. When the reaction stop although and no current flow through the cell, any further increase in external potential again start the reaction but in opposite direction. It is now function as an electrolytic cell, a device used for using chemical energy to carry non-spontaneous chemical reaction. Both types of cells are quite important as we shall study some of their silent feature in the following page. Galvanic cell. As mentioned earlier, a galvanic cell is an electrochemical cell that convert the chemical energy of spontaneous redox reaction. In this device, the Gibbs energy of spontaneous redox reaction is converted into electrical work, which may be used for running a motor or other electrical gadget like heater, fan, or geyser, etc. Daniell cell discussed earlier is one of such cell in which the following redox reaction occur. Zinc plus copper ion in aqueous solution gives zinc ion in aqueous solution plus copper in solid. This reaction is a combination of two half reaction whose 2 electron gives copper solid reduce half reaction and zinc gives zinc ion plus 2 electron, that is oxidation half reaction. These reactions occur in two different portions of Daniell cells. The written half reaction occur on the copper electrode while the oxidation half reaction occur on the zinc electrode. These two portions of the cells are called half cells or redox couple. The copper electrode may be called the reduced half cell and the zinc electrode the oxidation half cell. We have construct innumerable number of galvanic cell on the pattern of Daniell cell by taking combination of different half cell. Each half cell consists of a metallic electrode dipped into an electrolyte. The two half cells are connected by a metallic wire through a voltmeter and a switch externally. Electrolyte of the two half cells are connected internally through a salt bridge. Sometimes both the electrolyte dip in the same electrolyte solution, and in such cases we do not require a salt bridge. At each electrolyte, at each electrolyte interfere, there is a tendency of metal ions from the solution to deposit on the metal electrode, trying to make it positively charged. At the same time, metal atom of the electrode have a tendency to go into the cell or ions and leave behind the electron as the electrode, trying to make it negatively charged. At equilibrium, there is a separation of charges, and depending on the tendency of the two opposite reaction, the electrode may be positively or negatively charged with respect to the solution. A potential difference develops between the electrode and the electrolyte, which is called potential. When the concentration of all the species involved in a half cell is unity, then the electrode potential is known as standard electrode potential. According to IUPAC convections, standard reduction potential are now called standard electrode potential. In a galvanic cell, the half cell in which the oxidation takes place is called anode, and it has a negatively potential with respect to the solution. In other, the half cell in which a reduction takes place is called cathode, and it has a positively potential with respect to the solution. Thus, there exists a potential difference between the two electrodes as soon as the switch is in the on position, and the electron flow from negative electrode to positive electrode. The direction of the current flow is opposite to that of electron flow. The difference between the two electrode of a galvanic cell is called the cell potential and is measured in volt. The cell potential is the difference between the electrode potential reduction potential on the cathode and anode. It is called the cell electromotive force EMF of cell. When no current is drawn through the cell, it is now an accepted convention that we keep the anode on the left and the cathode on the right while representing the galvanic cell. A galvanic cell is generally represented by putting a vertical line between the metal and electrolytic solution and putting a double vertical line between two electrolyte connected by a salt bridge. Under this convection, the EMF of the cell is positive and is given by the potential of the half cell on the right hand side minus the potential of the half cell on the left hand, illustrated by the following example. Cell reaction: copper of silver gives copper ion and 2 Ag. Half cell reactions: cathode reduction, 2 Ag gives plus 2 electron gives 2 Ag solid. Anode oxidation: copper gives copper ion plus 2 electron. It can be seen that the sum of the reaction of 3.5 and 3.6 leads to the overall reaction of 2.4 in the cell. That silver electrode act as a cathode and copper electrode act as an anode. The cell can be represented as copper solid and copper ion in aqueous gives silver ion plus silver solid, and we have E cell is equals to E right minus E left, that is EAg plus by E minus E copper. Thus the potential of individual half cell cannot be measured. We cannot measure only the difference between the two half cell potential that gives the EMF of the cell. If we arbitrarily choose the potential of one electrode half cell and then the other can be determined with respect to this. According to convection, a half cell called standard hydrogen electrode represented by Pt H2 H plus ion is assigned as a zero potential at all temperature corresponding to the half H2. The standard hydrogen electrode consists of a platinum electrode coated with a platinum black. The electrode is dipped in an acidic solution and pure hydrogen gas is bulbed through it. The concentration of both the reduction and the oxidation form of hydrogen maintained by at unity. This implied that the pressure of hydrogen is 1 bar and the concentration of hydrogen ion in the solution is 1 molar. 98 Kelvin, the EMF of the cell, standard hydrogen electrode, double parallel line. Second, half cell construction by taking standard hydrogen electrode as anode, reference half cell, and the other half cell are as cathode, gives the reduction potential of the other half cell. If the concentration of the oxidation and reduction form of the species in the right hand half cells are unity and the half cell potential is equals to the standard electrode potential E naught R of the given half cell. E naught is equals to E naught R minus E naught L left, as EL for standard hydrogen electrode is 0. E naught is equals to E naught R minus 0 is equals to E naught R. The measure of the EMF of the cell Pt is equals to Ht 1 bar H plus ion 1 mole copper aqueous solution of 1 mole copper is 0.34 volt, and it is also the value for the standard electrode potential of the half cell corresponding to the reaction. Copper ion aqueous 1 mole plus 2 electron gives copper. Similarly, the measure EMF of the cell Pt plus H2 1 bar H plus aqueous solution of 1 mole zinc aqueous solution of 1 mole zinc is minus 0.76 volt. Corresponding to the standard electrode potential of the half cell reaction, zinc ion in aqueous solution of 1 mole plus 2 electron gives zinc solid. The positive value of the standard electrode potential is the first case indicate that copper ion get reduced more easily than hydrogen ion. The reverse process cannot occur. That is, hydrogen ion cannot oxidize copper, or alternative we can say that the hydrogen gas can reduce copper ion. Under the standard condition described above, the copper does not dissolve in HCl. In nitric acid, it is oxidized by nitric ion and not by hydrogen ion. The negative value of the standard electrode potential in the second case indicate that hydrogen ion can oxidize zinc or zinc can reduce hydrogen ion. In a view of this convection, the half reaction of the Daniell cell in figure 2.1 can be written as left electrode zinc gives zinc ion 2 plus aqueous 1 comma 1 mole plus 2 electron. Right electrode copper ion aqueous 1 mole plus 2 electron gives copper solid. The overall reaction of the cell is the sum of above two reaction, and we obtain the reaction zinc plus copper aqueous, and zinc gives aqueous plus copper. EMF of the cell is equals to E naught cell is equals to ER minus EL. ER is equals to 0.3 volt minus 0.76 volt, that is 1.10 volt. Sometimes the metal like platinum or gold are used as an inert electrode. They do not participate in the reaction but provide their surface for with half cell reaction. Half bromine aqueous solution plus electron gives bromine ion. The standard electrode potential are very important and we can extract a lot of useful information from them. The values of standard electrode potential for some selected half-cell reduction reactions are given in table 2.1. If the standard electrode potential of an electron is greater than 0, then its reduced form is more stable as compared to hydrogen gas. Similarly, if the standard electrode potential is negative, then hydrogen gas is more stable than the reduced form of the species. It can be seen that the standard electrode potential for fluorine is the highest in table, indicating that fluorine gas is the maximum tendency to get reduced to fluorine ion, and therefore fluorine gas is the strongest oxidizing agent and fluorine ion is the weakest reducing agent. Lithium has the lowest electrode potential, indicating that lithium ion is the weakest oxidizing agent, while lithium metal is the most powerful reducing agent in an aqueous solution. It may be seen that as we go from top to bottom in table 2.1, the standard electrode potential decrease with and with this decrease the oxidizing power of the species on the left and increase the reducing power of the species on the right side of the reaction. Electrochemical cells are extensively used for determining the pH solution solubility, product equilibrium constant and other thermodynamic properties, and for potentiometric. We have assumed in previous section that the concentration of all the species involved in electrode reaction is unity. This need not always be true. Known as so for electrode reactions, M plus aqueous solution plus Ne gives M in solid. The electrode potential at any concentration measured with respect to a standard electrode can be represented by E is equals to E naught minus RT by NS if M upon Mn plus. But concentration of solid M is taken as a unity, as we have to Mn plus by M is equals to E naught minus RT by NF in 1 by Mn plus. E naught Mn plus by M has already been defined as R constant, which is 8.314 Jk per mole. F is the Faraday constant 96487 Coulomb per mole. T is the temperature in Kelvin, and Mn is the concentration of the species Mn. In Daniell cell, the electrode potential of a given concentration copper and zinc ion we write for cathode E is equals to E naught, that is copper minus RT by 2F in 1 by copper ion in aqueous solution. In anode for zinc, E is equals to E naught minus RT by 2F in 1 by zinc ion in aqueous solution. Cell potential E cell is equals to E copper minus E zinc to RT by 2F in 1 by copper minus E naught is equals to zinc plus RT by 2F in 1 by zinc ion. E is equals to E naught minus E naught zinc, copper minus zinc ion minus RT by 2F in 1 by copper ion equals solution minus in 1 by zinc ion in aqueous solution. E cell is equals to E naught minus RT by 2F in zinc ion by copper ion. It has seen that E cell depends on the concentration of both copper ion and zinc ion. It increases with increase in the concentration of copper ion and decrease in the concentration of zinc ion. By converting the natural logarithm in equation 2.11 to the base 10 and substituting the value of R, S and T is equals to 298 Kelvin, it reduced to E cell is equals to E naught cell minus 0.059 by 2 log zinc ion by copper ion. We should use the same number of electrons N for both the electrodes, and thus for following cell
Nickel solid by nickel iron aqueous, silver aqueous by silver. The cell reaction is NiS plus 2Ag plus aqueous that gives to Ni2 plus aqueous plus 2Ag solid. The Nernst equation can be written as E cell is equals to E naught minus RT by 2F in nickel iron by silver iron. For a general chemical reaction of the type A plus B that gives C plus D can be written as E cell is equals to E naught minus RT by NF in Q, E naught by RT by NF in C by D upon A into V. Constant for Nernst equation. In the circuit in Daniell cell, figure 2.1 is closed and we wrote note that the reaction zinc plus copper gives zinc iron and copper. Take a place of NT as the place time passes. The concentration of zinc keeps on increasing while the concentration of copper keeps on decreasing. At the time, voltage of the cell as reads on the voltmeter keeps on decreasing. After some time, we shall note that there is no change in the concentration of copper and zinc ion, and at the same time, voltmeter gives zero reading. This indicates that equilibrium has attained. In this situation, the Nernst equation may be written as E cell is equals to 0, E naught cell minus 2.303 RT by 2F, log zinc ion by copper ion, or E naught is equals to 2.303 RT by 2F log zinc ion by copper ion. But at equilibrium, and is equals to Kc for reaction 2.1 at temperature T 298 Kelvin. The above equation can be written as E naught cell is equals to 0.059 volt by 2. Log Kc is equals to 1.1 volt. E naught cell is equals to 1.1 volt. Log Kc is equals to 1.1 volt into 2 upon 0.059 volt. 373.288. Kc is equals to 2 into 10 to power 37 at 298 Kelvin. In general, E naught cell is equals to 2.303 RT by NF log Kc. Thus, equation 2.14 gives the relationship between equilibrium constant of the reaction and standard potential of the cell in which the reaction takes place. Thus, equilibrium constant of the reaction difficult to measure. Otherwise, we can calculate for the corresponding E naught cell of the E naught value of the cell. Electrochemical cells and Gibbs energy of the reaction. Electric work done in 1 second is equals to the electric potential of multiplied by total charge passed. If we want to obtain maximum work for a galvanic cell, then charge has to be passed reversely. The reversible work done by a galvanic cell is equal to the decrease in its Gibbs energy, and therefore, if the EMF of the cell is E and NFF is the charge passes and Gibbs energy gives del naught R is the Gibbs energy of the reaction, then Gibbs energy is equal to minus NFE cell. It may be remembered that E cell is the intensive parameter, but Gibbs and del G is the extensive G is an extensive thermodynamic property and the value depends on N. Thus, if we write the reaction zinc plus copper ion gives zinc ion plus copper, gives energy give, del G is equal to minus 2Fe cell. When we write the reaction 2Zn plus 2 copper ion gives 2Zn plus 2 copper, gives energy is equals to minus 4Fe E cell. If the concentration of all the reacting species is unity, then E cell is equals to E naught cell and we have del G naught is equals to minus NF E naught cell. Thus, for measurement of E naught cell, we can obtain an important thermodynamic quantity del G naught standard gives energy of the reaction. For the later, we can calculate equilibrium constant by the equation del G naught is equals to minus RT in K. Electrolytic solution. It is necessary to define a few terms before we consider the subject of conductance of electricity through electrolytic solution. The electrical resistance is represented by the symbol R and it is measured in ohm, which is represented by this symbol, in which in terms of SI basis unit is equals to kg meter square by S cube A square. It can be measured with the help of Wheatstone bridge, with which you are familiar for studying your physics. The electric resistance of any object is directly proportional to length and inversely proportional to area of cross section A. That is, R is directly proportional to L and inversely proportional to A. R is equals to rho L by A. The constant of proportionality rho, Greek rho, is called resistivity or specific resistance. Its SI unit is ohm meter and quite often its sub multiply ohm meter, ohm centimeter is also used. IUPAC recommended resistivity over specific resistance and hence in rest of the book we shall use the term resistivity. Physically, the resistivity of a substance is the resistance when it's 1 meter long and its area of cross section is 1 meter square. It can be seen that 1 ohm meter is equals to 1 ohm centimeter, or 1 ohm centimeter is equals to 0.01 ohm meter. The inverse resistance R is called conductance, and G, and we have the relation G is equals to 1 by R is equals to A by rho L is equals to K A by L. The SI unit of conductance is Simon, represented by the symbol S, and is equals to ohm per meter, also known as mho, or ohm square. The inversion of the resistivity, called conductivity, specific resistance, is represented by symbol K, Greek kappa. IUPAC have recommended the term use of conductivity over specific conductors, and hence we shall use the term conductivity in the rest of the book. The SI unit of conductivity S by M, but quite often K is expressed in S by centimeter. Conductivity of a meter is S by M. Its conductance, where it is 1 meter long, and its area of cross section is 1 meter square. It may be noted that 1 S is S by 100 S by M. Given the table 2.2, the value of conductivity of some selected material at 298.15 Kelvin. So here are giving some materials and their conductivity, that is represented by S by M. ओके, कंडक्टर, इंसुलेटर, एक्वा सोल्यूशन एंड सेमी कंडक्टर सब दिए हुए हैं, साथ में उसकी कंडक्टिविटीज भी दी हुई हैं, तो यहाँ पे आप किसे पढ़ सकते हैं. It can be seen from table 2.2 that the magnitude of conductivity varies a great deal and depends on the nature of the material. It also depends on the temperature and pressure at which the measurement of are made. Materials are classified into conductor, insulator, and semiconductor depending on the magnitude of their conductivity. Metals and their alloys have a very large conductivity and known as conductors. Certain non-metals like carbon black, graphite, and some organic polymers are also. Earlier, only metals and their alloys at very low temperature, 0 to 15 Kelvin, were known to behave as superconductor. But nowadays, a number of ceramic material and mixed oxides are also known to show superconductivity at temperature as high as 150 Kelvin. Electrical conductance, though material is called metallic or electronic conductance, and is due to the movement of electrons. The electronic conductance depends on the nature and the structure of the metal, the number of the valence electron per atom, temperature. It decreases with increase of temperature. Conducting polymer. In 1977, McDermott, Harrier, and Shrikawa discovered that acetylene gas can be polymerized to produce a polymer. Polyacetylene, when exposed to vapor of iodine, acquires metallic luster and conductivity. Since then, several organic conducting polymers have made, such as polyaniline, polypyrrole, and polythiophene. These organic polymers, which have properties like metal, being composed wealthy of elements like carbon, hydrogen, and occasionally nitrogen, oxygen, and sulfur, are much higher than normal metals and can be used for making lightweight batteries. Besides, they have mechanical property of polymers such as flexible, so that one can make electronic device such as transistor that can be bent like a sheet of plastic. For the discovery of conducting polymer, Matt Harrier and Sri Kawa were awarded by the Nobel Prize in Chemistry for the year 2000. Enter at one end and go out through the other end, and the composition of metallic conductor remain unchanged. The mechanism of conduction through semiconductor is more complex. We already know that even very pure water has small amount of hydrogen and hydroxyl ion, 10 to the power minus 7 m, which lends its very low conductivity, 3.5 into 10 to the power minus 5 units by m. When electrolytes are dissolved in water, they furnish their own ions in the solution, and hence its conductivity also increases. The conductance of electricity by ion present in the solution is called electronic or ionic conductance. The conductivity of electrolytic ionic solution depends on nature of electrolytic ads, size of the ion produced, and their solvation, nature of the solvent and the viscosity, concentration of the electrolytes. It increases with increase of temperature. Passage of direct current through ionic solution over a prolonged period can be leads to change in its composition due to electrochemical reaction. Measurement of conductivity of ionic solution. We know that accurate measurement of unknown resistance can be performed on a Wheatstone bridge. However, for measuring the resistance of an ionic solution, we face two problems. Firstly, passes passing direct current DC changes the composition of solution. Secondly, a solution cannot be connected to bridge like a metallic wire or other solid conductor. The first difficulty is to resolve by using a AC source of power. The second problem is solved by using a specifically designed vessel called conductivity cell. It is available in several designs and two simple ones are shown in figure 2.4. Different type of conductivity cells. This is figure 2.4. Basically, it consists of two platinum electrodes coated with platinum black. Finally divided metallic platinum is deposited on the electrodes electrochemically. These have area of cross section equals to A and are separated by distance L. Therefore, solution confined between these electrodes is a column of length L and area of cross section A. The resistance of such a column of solution is then given by equation R is equals to rho L by A is equals to R L by Ka. L by A is called cell constant denoted by capital G. It depends on the distance between the electrodes and their area of cross section has the dimension of length and can be calculated if we know L by L and A. Measurement of L and A is not only convenient but also unreliable. The cell constant is usually determined by measuring the resistance of cell containing a solution whose conductivity is already known. For this purpose, we generally use KCl whose conductivity is actually accurate at various concentrations and at different temperature. The cell constant that is capital G is then given the equation capital G is equals to L by A is equals to R by K where K is constant. Molar conductivity of K solution at 298.15 Kelvin. So here is given concentration and here is given molarity. Here is given conductivity and here is given molar conductivity. Once the cell constant is determined, we can use it for measuring the distance or conductivity of any solution. The setup for the measurement of the resistance is shown in figure 2.5. It consists of two resistors R and R4 and variable resistance R1 and the conductivity cell having the unknown resistance R2. The Wheatstone bridge is fed by an oscillator O. A source of AC power is the audio frequency range from 550 to 5000 cycle per second. P is a suitable detector. A headphone or other electronic devices in the bridge is balanced when no current passes through the detector. Use these conditions. Unknown resistance R2 is equals to R1 into R4 by R3. And these days, inexpensive conductivity meters are available which are directly read the conductance or reactance of the solution in the conductivity cell. Once the cell constant in the resistance of solution in the cell is determined, the conductivity of the solution is given by the equation K is equal to cell constant by R that is capital G by R.